Welcome, everyone. How are you doing? Great. Let's talk about engineering cinematic VR, or in other words, immersive VR video experiences. I'm Hussein, a product manager working on VR video, and today we're going to talk to you about some of the challenges associated with the medium, focusing primarily on delivery and playback. Let's start with why we think VR video is important. VR video has the power to immerse you and transport you to events, places, and moments, and make you feel like you're there. It's a kind of immersion that traditional video on a rectangular screen can't quite get you. For a start, there's too much of the real world visible on the periphery. With VR video, your entire field of view is occupied with nothing but the content. If I were watching this scene in VR, I might actually feel like the horse was looking directly at me. That sort of immersion you just can't get by watching a TV. Now, in the real world, I can look around, and VR video enables that too. In order for it to feel like I can reach out and touch that horse, though, I need to be able to perceive a sense of depth and scale. And that comes through stereoscopic 3D, in which each eye sees a slightly different image. Take a look at the horse and focus on its face and the window right behind it, and watch as I toggle the image your left eye would see with the image your right eye would see. That small but important difference is exactly how we perceive depth in the real world. It's what makes near things look near and far things look far. Adding this into 360 video is incredibly immersive, and it is almost as important as the ability to look around. So far, we've only talked about video, and we've still come a long way from that flat TV screen I showed you at the beginning. However, we haven't even approached audio yet. In a stable, I would expect to be able to hear the horses around me. And if we did that through traditional audio effects, it might feel incomplete. Here's why. Turn your head and look around the room. You'll notice that sounds around the room, like that fan for instance, sound slightly different as you turn your head. And that actually enables you subconsciously to be able to localize where that sound was coming from, even if your eyes were closed. We can recreate that in VR through the use of spatial audio. Now let's add all of this together. 360 video with stereoscopic 3D watched in VR so you can perceive it, and spatial audio. And we think you have all the elements needed for cinematic VR experiences, or VR video that can truly transport you. At Google, our mission is VR for everyone, which also means VR video for everyone. We wanted to find a way to overcome the engineering challenges associated with the medium in a way that makes these experiences available to as many people as possible. We started by building Jump, our VR video creation platform. It consists of a camera spec that partners are helping bring to market, an assembler that takes away all the pain of manual stitching, and finally, a way to play back that VR video alongside spatial audio on a platform that you all are already familiar with. You can watch many of these incredible experiences on YouTube today. But that's not all. Behind the scenes, we've been working to make playback of these types of videos even better. To talk to you about that, I'd like to invite up on stage Andrew Shirkus. Come on up, Andrew.
Thanks, Hussein. Hey, everyone. I'm Andrew Shirkus, and I'm going to talk a little bit today about some of the tech we've been building to really create that immersive VR video experience. But what do I really mean when I'm saying immersive VR video? Well, in our opinion, it comes down to a few key ingredients. First of all, you want to have as much resolution right in front of where you're looking. This really creates that first important ingredient of making it feel like you're right there. But as Hussein mentioned, we're huge believers in stereo. And so we'll need to double that resolution just to actually give you that stereo imagery. Because without stereo, we don't think it really counts. It doesn't really feel like you're there. And finally, and perhaps most importantly, No buffering at all. It's one thing to have your phone out and be waiting for like a video to load. When it's glued to your face, it is a horrifying experience. So we need to be really bandwidth conscious and worry about connectivity. So with that in mind, let's walk through some steps on how would we actually create immersive video. Well, we're working with 360 video, so first of all, we have to pick some way to represent it. So we'll pick a sphere to plane projection to represent our video. We'll increase the resolution until we're fully filling up the screen in your optics so that you can see everything in full fidelity. And then we're going to double it because we love stereo. So let's dive into that first piece, that sphere to plane projection. It turns out, if you've ever looked at a map, this is a pretty familiar concept. Seen here is your good old-fashioned equirectangular projection of the Earth. And even though this has been used for quite some time, it's actually a pretty useful format today and is actually used for your 360 cameras, both for images and video alike. Here's a sample frame. And sure, it's a little funky looking at the top and bottom, but you get a good sense for what's going on, right? I'm over there on the left, and I'm reaching towards the camera, and my fingers kind of get all mushed up, but you get it, right? You can kind of figure out what's going on. And 360 cameras produce this format today, and streaming video sites like YouTube accept this format today. You could even take this and put it into a video editing app, and you could kind of stitch together a basic film. It kind of works. But let's do some back of the envelope math to figure out just how big an equirectangular video would have to be in order to give you that first requirement of really filling up the maximum resolution. So let's assume we have a 1440p display. It's pretty common on high-end smartphones. We'll divide it by 2 to get 1280 pixels. We'll assume, just to make the math easy, around 100 degrees field of view for your headset. This gives us about 12.8 pixels per degree. Then you multiply it by the sphere around the horizon, which is 360 by 180. And this kind of gives us an approximation to really hit that maximum resolution we're talking about. So to put that in terms of like megapixels, just for comparison, this brings us to 10.6 megapixels for mono. But I'm really driving this home. We love stereo, so we got to double it. That puts us at 21.2. And for reference, a 4K stream is 8.3. So we're way over budget. Not only is this going to be really hard for a hardware decoder to do, it's also really hard for like a multi-core desktop workstation to do. And not only that, but I feel like you're going to be seeing a lot of that buffering spinner. So this is not really going to work. This is where equirectangular just like totally falls flat on its face. But luckily, we don't have to stick to it, right? Once you upload it to like YouTube, we can work with that, right? We can work with these big files. To cover sort of why projections are challenging, it really boils down to the math behind sphere to plane projections. If I were to tell you to take an orange and unpeel it and try to make it look like a rectangle, you actually can't do it without flattening and squishing and stretching that peel. So what that means is the visual quality starts to change based on where you've stretched in order to make that rectangle. So if the user looks in some areas, it'll look better. And when they look in other areas, it looks worse. So when we looked at this, we really wanted to consider all the best and worst qualities of any given projection. Let's go back to Earth. So there is a huge, glaring, obvious clue on the map of any Earth that kind of really gives you a hint on where the best quality might be. And it's at the poles, right? Antarctica is ginormous, but it's not that ginormous of a continent. Correspondingly, the worst visual quality is along the equator. If we consider 360 imagery, this doesn't make a lot of sense, right? My fingers are getting a lot of pixels, and the ceiling is getting a ton of pixels too, but where everyone is standing, they're not getting their fair share of pixels. That's not a great solution. So going back to what I mentioned earlier, what if we use something else, such as cube maps? You may have seen this in games. Anytime you walked around and you wanted to have the sky appear something or to have environmental effects. You'll immediately notice that Antarctica looking a lot more regular sized compared to everything else. This is already a great first clue that, hey, things might be a little bit more uniform. But it starts to get tricky, right? With equirectangular, we were really easily able to figure out that, okay, the top and the bottom gets the most pixels and the middle gets the least. How do we analyze projections such as cube map? And expanding upon that, how do we analyze any arbitrary projection? So we built some analysis tools to really deeply understand this problem. This is the spectrum that we're going to use to sort of describe these projections. On one end, we've got too much upscaling going on. This means that if someone were to look in a region that's kind of more reddish or orangish, it'll be blurry. On the other end of the spectrum, we have too much downscaling, which typically isn't always a bad thing, but if you think about it in the sense of bandwidth and trying to really nail the right quality without serving too much, you don't actually want too much downscaling going on. It's a wasteful thing. So there is a sweet spot, and it's for a given resolution for a given hardware display and optics combo. Let's take a look at what equirectangular looks like with our tool. Right off the bat, we see at the top and bottom, we got that blue. I'm sure it looks great. I'm sure my feet look wonderful, but that's not really the point of 360 video. If we were to look at cube maps in this tool, we start to see a more interesting, colorful picture. And ironically enough, we represent these images in equirectangular format because they're just human friendly. You'll start to notice that the best visual quality when using cube maps are along the edges. This means that if you took a 360 video in a cube map, and I were to try to quiz you on, hey, where to look for the best quality, you would actually tilt your head to the left and tilt it up. And you would look in one of the corners, because that's actually where the best image quality is hiding. Correspondingly, the worst areas of a cube map are right in the middle of each face. When we started looking at pictures like this, we were like, I wonder if there's something else we could use. And we did some digging, and it turns out that people have been looking at projections for a long time. And there was one that was used with actual space imagery in the 70s, and we called it equiangular cube map. The basic concept is just to take some of those extra pixels that were in the corners and sides and just kind of spread them around a little bit more. We end up with actually a much more uniform representation of the full sphere. When we test this with users, every single person was able to tell that they're like, yep, that looks better. I don't know why, but I just like it better. That made us feel pretty good. So it doesn't quite get us there though, right? We've been only looking at very uniform representations, very uniform projections. And this is a pretty good solution. You can use this for images or video to get that really nice uniform resolution everywhere you look. And it's a good candidate for offline or unreliable bandwidth. You only need to create one of these videos and just buffer it for as long as you want. But it doesn't hit that sweet spot we were talking about earlier. So how are we going to get there? Where can we really just leverage the user gaze and the user view direction to deliver as many pixels as possible to where they're looking? With projections, you can actually represent them as 3D geometry. So with equirectangular, you can map it to a tessellated 3D sphere. With a regular cube map, you can map it to a cube. Kind of makes sense. And with something like equiangular cube map, you can map that to a tessellated cube. But what if we went with something a little bit more exotic? What would that look like in our analysis tool? We were kind of curious. So for fun, let's just take a look at pyramid. Right off the bat, it's pretty colorful. And you'll notice that the best visual quality is right smack dab in the middle. This is pretty awesome. And that things kind of just gradually taper off. And that's not necessarily a bad thing. This is a simulation of what that original frame would look like. I'm nice and clear. My co-presenter, Dylan, we would have to generate a new video to actually sort of represent him, because in the previous version, he was kind of blurry. And same, we'd have to generate a new video with a new pyramid if we wanted to focus on the group of people to the right. So we like to call these class of projections directional projections, right? They're very directed towards a particular region, and they place the highest resolution within a particular field of view. On the flip side, like I just illustrated, it does require multiple versions, right? If there are multiple regions of interest, you have to generate multiple videos. And to keep up with that immersion, we really want to have low latency and minimal buffering. Because if it takes a couple seconds and I'm seeing blurriness over here, that kind of kills the whole experience. So to kind of summarize all of this talk about projections, we really feel like there isn't necessarily a silver bullet here. It really depends on the content, where people are looking, your bandwidth, and actually the characteristics of the hardware. So with that in mind, it really kind of starts to make you think about, well, how do you tie this into existing video streaming sites like YouTube today? And we found it really helpful to look at how this was solved with multiple resolution streams, or adaptive streaming. Here's a super simple example with just a standard definition and high definition stream. Based on your bandwidth or your device, you would either get switched up to a high definition stream or back to a standard definition stream. And if your device actually can't even play HD content, it also doesn't really necessarily mean it makes a lot of sense to serve you HD content. And same with if your bandwidths all of a sudden start to get a little unreliable, we'd want to switch you back because we don't like buffering. Right? Adaptive streaming is a really great solution at minimizing any instances of buffering. With this model in mind, we actually kind of applied it to our whole notion around there not being a single projection to rule them all. And we call it adaptive projection streaming. We really noticed that there are instances where you really do want that uniform projection, notably to avoid buffering. But there are also instances where you really want that sharp focus in a particular area, whether it's due to the content or whether it's just due to the user just looking in a particular direction. We actually find tying things together this way makes it really easy to reason about and solve a lot of different use cases. Because again, we really care about delivering as much of VR video to as many people as possible. So we're actually building this in YouTube today. And even if a lot of this kind of projection stuff was like, oh, I really don't want to deal with pyramids or this equiangular something or other, like that's totally fine because we have equirectangular. It's going to be here for like a while, right? The map didn't go anywhere. You can upload your content to YouTube. We'll kind of take care of the rest and make it look the right kind of shape and size to deliver the goal of really immersive VR video for everyone. That only really covers the video aspect, though. I'm going to bring up Dylan here. He's going to talk to us a little bit more about audio.
Thanks, Andrew. So Andrew talked to you about what we're working on to improve the visual quality of cinematic VR experiences. That's only 50% of the experience. So today, I'm going to be talking to you about what we're doing to bring awesome spatial audio to cinematic VR experiences for everyone. Our ears are highly complex instruments, taking in a vast amount of information every point in time. And as such, they're a critical tool for VR storytelling. VR needs spatial audio. We really believe that. So what is spatial audio? What it boils down to is audio that fully represents the sound space around the listener. It allows the listener to answer a couple of questions. Where is the sound coming from? In what environment am I in? So spatial audio should have three properties. It should have a location in space. It should capture the environment. And finally, it should immerse the listener. At the end of the day, you should feel like you've teleported somewhere else, and everything should look and sound correct and amazing. We really think that you can't feel presence without hearing it. So let's think for a second about the bare minimum amount of information that we would need to stream to the client for them to hear spatial audio. Well, humans have 2 ears. And in VR, we're generally using headphones to listen to the audio. So maybe we can just stream that. We can stream 2 channels of audio. So in theory, you could store a complex representation of the spatial audio seen on the server, and then render that in real time on the server, depending on where the listener is viewing, and then stream that to the client. And this is a pretty well understood problem from the streaming point of view. It's equivalent to streaming stereo audio. However, in reality, this doesn't work out. There's latency everywhere in the stack, in audio encoding, audio decoding, audio output, network transmission, and so on. And what this adds up to is just a poorer VR experience. So we know that we need to find a representation for spatial audio to send to the client. We know that we can't just pre-render 2 channels of audio and send that. We need to represent the full audio scene. So let's start off by taking a look at surround sound audio, 5.1, 7.1, traditional speaker layouts. And surround sound audio is based around this idea of each channel of audio corresponding to a physical speaker. So for 5.1 audio, you'll have 6 channels of audio for 6 physical speakers. Front left, front right, center, and so on. However, surround sound is built for front-facing experiences, like home cinema or theaters. And this is great for that application, where most of the action is in front of you, and there's not so much behind you. And so the speaker layouts are oriented toward this, with more speakers in the front and fewer in the back. However, for VR, this isn't ideal. We care just as much about audio behind you as we do audio in front of you. And in addition to that, speaker layouts for surround sound audio are generally pretty horizontal. There's not a lot of vertical resolution there. And in 360 video, we care about everything in the sphere. So let's now talk about object-based audio. And the idea here is to represent everything in the scene. For each source, we're going to take mono audio along with metadata about that source, its position, size, speed, shape, and so on, as well as characteristics about the environment, such as reverb, reflections, geometry, as complex as we want. But this sounds like an audio engine for games, and it basically amounts to that. And this is great for interactive experiences, where depending on user input, you want to change the way that things sound. You might want to play a sound over here, or you might want to attenuate something depending on where the viewer is looking. And this is also great for post-production and mastering, where you want the highest fidelity spatial audio representation that you can have. Now, for streaming, we love predictability and we love consistency and data rate. It allows us to adapt better to the user's bandwidth, and in general, we just like that. And for VR as well, we like predictability and we like consistency and performance. We want each of our frame times to be as close as possible. However, with object-based audio, as the number of sources in the scene increases, or as the environment changes, more data is required. And this isn't good for streaming. So finally, let's take a look at Ambisonics. And Ambisonics is a full sphere spatial audio representation, dating back to the 70s, where it was far ahead of its time. And the idea behind Ambisonics is opposite to object-based audio. Object-based audio, you store everything about the scene. With Ambisonics, you're collapsing that down into an approximation of the scene. So you don't want to store the entire scene, you just want to store some kind of approximation of it. And this is great for streaming because it hits those points of consistency and predictability. So let's take a look at first-order Ambisonics, which is the initial version of Ambisonics. The idea is similar to mid-side stereo, which is a technique used in the audio industry. And the idea behind mid-side stereo, you take 2 microphones, and then you sum them in different ways to create a narrow or a wide stereo image. So first-order Ambisonics can be seen as an extension of this in 3 dimensions. Instead of 2 microphones, we're talking about 4 microphones now. An omnidirectional microphone and 3 figure-8 microphones. And then you combine these in different ways, similar to mid-side stereo, to create virtual microphones on the sphere. So we can hear audio as it is in front of you, to the right of you, or anywhere else. And we can smoothly rotate between these positions. And Ambisonics is also based on a concept called spherical harmonics. And the idea behind spherical harmonics is we're trying to approximate a spherical function, a function on the surface of a sphere. So each of these morphed spheres you see is called a spherical harmonic. And each one of those maps directly to an ambisonic audio channel. That's a channel of ambisonic audio. And the lobes that you see, the shapes, they're similar to microphone directivity patterns. And microphone directivity patterns tell us the sensitivity of a microphone to sound coming from different directions. So the omnidirectional harmonic here is sensitive to sound uniformly from all directions, whereas the left-right component is more sensitive to sound from the left and right than it is from the front, back, or the top and bottom. So just to recap, the idea behind Ambisonics is we're going to take the entire spatial audio scene, no matter its complexity, no matter the number of sources, no matter what the environment is. Then we're going to collapse that down into an approximation, and we're going to break that into separate components to represent that approximation. And then in real time on the client, we're going to combine that approximation to create virtual microphones on the sphere. And this allows us to hear audio in any direction, so we can respond to viewer head rotation in real time. So first order ambisonics is pretty great. It really increases immersion, and you start to feel like you're there. But there's room for improvement. With first order ambisonics, there's a fairly large margin of error. Pinpoint audio sources don't sound so pinpoint. They're widened. And it's hard to actually locate a source perfectly without a visual cue to guide you. So our solution here is spherical harmonics. So as I mentioned before, spherical harmonics is mathematically based. And it has this nice property that's infinitely extensible. So we can choose our cutoff point. If we want only one harmonic, we can do that, the omnidirectional component. Or if we want 4 for first order ambisonics, we can do that as well. Or if we want 16 components of audio, we can do that, and that's called third order ambisonics. And that actually starts to sound pretty freaking great. There's a dramatic increase in quality over first order ambisonics. Things sound crisper, more precise, just better overall. And it increases immersion even further. However, I haven't even talked about how to stream ambisonics to the client. So let's take a look at that for a second. So again, our goal here is spatial audio for everyone. No matter where you are in the world, or no matter your bandwidth or device, we want to stream spatial audio to you, and we want you to have that great cinematic VR experience. However, traditional audio technology is not built for ambisonics. It's built for stereo audio. And this is great for the past, where stereo audio makes a ton of sense, but in VR, it's decreasingly making sense. So we wondered, is there some existing technology that we can repurpose to stream ambisonics? And there is, and it's called Vorbis, which is a free and open audio codec. So we take first order ambisonics, omnidirectional, up, down, left, right, and front, back, spherical harmonic components, and then we stuff that into a quadraphonic layout, front left, front right, back left, and back right. And this actually is pretty good. Multi-channel Vorbis support is great across a number of platforms, and this helps us hit our goal of VR for everyone. However, this isn't ideal for a couple of reasons. Ideally, with ambisonics, we want a different bit distribution than what we have right now. With the quadraphonic layout, we have a uniform bit distribution, so each of the audio channels gets the same number of bits allocated to it. However, with ambisonics, we'd like to dedicate more bits to the omnidirectional channel than we do the others, because the omnidirectional channel encompasses the entire sphere, so it's used all the time. And for higher order ambisonics, it's not really clear how you're going to do that with a traditional codec. The data rates get pretty crazy, and we're not really sure that that's going to help hit our goal of streaming VR spatial audio for everyone. So we're working on it. We're working on higher order ambisonics compression using Opus, which is a free and open modern audio codec. So what higher order ambisonics streaming via Opus will allow us to do is stream high fidelity spatial audio to more people, getting more ears than we can today, at significantly lower data rates. So I've talked about streaming spatial audio and what spatial audio is, but I haven't gone into creation at all. And I actually won't go into creation very much today. We have resources online for that. But in general, creating spatial audio is hard, and creating VR video in general is hard. Today, it requires a number of tools, and the iteration cycles are pretty long. So we're working on that as well. We've developed Jump Inspector, which is an Android app for cardboard, which allows you to preview VR videos with spatial audio in real time on your Android device. And Jump Inspector also has a great feature for spatial audio producers called Jump Inspector DAW integration. And what that allows you to do is sync Jump Inspector to your digital audio workstation so you can mix in real time and preview VR video on your device in cardboard as you're mixing, as you're adjusting levels. Anything you do in the mix is rendered in real time in sync with Jump Inspector, and it's pretty great. And lastly, if you want to check out spatial audio today, you can. Just go to the YouTube 360 channel on your Android device, pop it into cardboard, have a listen, let us know how it goes. And now back to Hussein to talk a bit about what we're doing for fostering a healthy VR ecosystem. Hussein?
Everything we've talked to you about today so far, our investment in Jump to make VR video creation easier, playback improvements through adaptive projections, and our work on spatial audio. All of these are rooted in a belief that VR video done well and delivered at a high quality can make some of the most powerful VR experiences possible today. There's one more thing I want to talk about, formats. We believe having an open and easy-to-use format is critical to the success of the ecosystem. It's been great to see that one of the formats we published in 2014 has gotten a reasonably wide amount of adoption. We've also received a lot of feedback, though. And we've taken a lot of that feedback into account and published a greatly simplified version of the format at our GitHub repository earlier today. You can find that, along with instructions on using Jump Inspector, and a pointer to a discussion group where anyone can provide feedback on our format at that URL. At Google, we're committed to an open and strong VR video ecosystem. VR video for everyone. With that, I'd like to wrap up. Thank you all so much for coming. My co-presenters and I will be sticking around to take questions offline. Otherwise, enjoy the rest of I/O. Thank you.